All right, strap yourselves in because we are taking a deep dive today into the physics of a simple pendulum.
Yeah, it should be fun.
We've got an awesome website here from Open Educational Resources, Open Source Physics at Singapore.
Mm-hmm.
They've got an interactive simulation that we're going to be looking at some learning goals.
Nice.
So you can actually play around with this pendulum along with us.
Oh, cool.
The URL is http://tinyurl.com/2016-4.
Sweet.
And don't worry, we'll walk you through everything.
Yep.
There are even two types of graphs to help us visualize the energy.
Oh, cool.
They're called E-bars and EVST graphs.
Okay.
But more on those a little bit later.
What's really cool about this is that the simple pendulum is like a mini lab for understanding how energy transforms.
Oh, yeah.
It's a great way to see the fundamental principles of energy in action,
Yeah.
principles that apply to systems all around us.
Right. So before we go too far, let's start with the basics.
Okay.
A pendulum, in its simplest form, is just a mass, which is called the bob, hanging from a fixed point by a string or a rod.
Right.
You give it a little push, and it swings back and forth.
Simple. Right.
Simple. But there's a lot more going on than meets the eye.
Totally.
And that's where the interactive simulation comes in.
Exactly.
Go ahead and open it up. If you've got a computer or your phone nearby,
Yeah.
I'll wait.
Yeah.
You'll see that you can actually adjust the initial angle of the swing,
Mm-hmm.
which is labeled theta, and the length of the string, which is labeled L.
Okay.
Just play around with those for a minute.
Yeah.
And just get a feel for how the pendulum behaves.
Yeah. Have some fun with it.
Now, while you're swinging that virtual pendulum around, let's talk about the two main types of energy that are at work here.
Okay.
Potential energy and kinetic energy.
All right.
So potential energy is all about the bob's position.
Okay.
Think of it this way. When you lift something up,
Mm-hmm.
you're giving it potential energy.
Right.
The higher you lift it, the more potential energy it has.
Makes
So where do you think the potential energy of the pendulum is the highest?
That's a good question.
It might be a little bit counterintuitive.
Yeah, I was going to say it's a bit counterintuitive for some people, but the potential energy is highest at the very ends of the swing when the pendulum is, kind of momentarily at rest and at its highest point.
Right.
Think about it like this.
Okay.
The pendulum is about to fall.
Mm-hmm.
It has the potential to move.
Right, exactly.
So even though it's not moving right at that second, it has the potential to...
Right. It's got all that stored up energy ready to go.
Yeah.
And then we've got kinetic energy, which is the energy of motion.
Right.
The
Yeah.
faster something moves, the more kinetic energy it has.
Mm-hmm.
So using that logic, where do you think the kinetic energy of the pendulum is the highest?
I think I know this one.
Okay.
It would be at the bottom of the swing when the bob is moving the fastest.
Exactly.
It's, zooming right through that middle point.
Yeah, and the source material even points out something really cool, that if you increase that initial angle or the length of the pendulum in this simulation,
Okay.
you'll notice that both the maximum potential energy and the maximum kinetic energy increase.
Interesting.
It's kind of like giving it more energy to play with, but the total amount of energy stays the same.
Okay.
It just transforms back and forth between potential and kinetic.
Right. So now is a good time to check out that E-bars graph in the simulation.
Oh, yeah, totally.
This graph actually visually shows us the amount of potential and kinetic energy at any given moment during the swing.
Okay.
You'll notice that as the pendulum swings, the bars representing potential and kinetic energy kind of grow and shrink.
Yeah.
But the total length of the bars always stays the same.
Right. And this is a perfect illustration of that principle of conservation of energy.
Yes.
That energy can't be created or destroyed. It can only be transformed from one form to another.
Exactly. Yeah.
This is a fundamental law of physics.
Absolutely.
Now let's put on our thinking caps
Okay.
and do a little bit of calculation.
Right.
In the modeling energy section, you'll see a table.
Mm-hmm.
Notice that they give us the mass of the bob, 1 kilogram,
Okay.
and remind us that the acceleration due to gravity is 9.81 meters per second squared.
Right.
But then they leave the table blank.
No.
So this is where you get to be the scientist.
Oh, fun.
You're going to calculate the potential energy at different heights
Okay.
using the formula PE,
Mhm.
where M is the mass, G is gravity, and H is the height.
Gotcha.
So to get you started, let's just take a height of, let's say, 0.2 meters.
Okay.
Using our formula, the potential energy would be
Mm-hmm.
1 kilogram times 9.81 meters per second squared
Mhm.
times 0.2 meters equals 1.962 joules.
So that's our PE.
Now it's your turn to go and fill out the rest of the table.
All right, let's do it.
So you think you've got a handle on the basics.
I think so, yeah.
Good. Because the source material then throws down a challenge.
Oh.
They call it rules of the game. And they give us the first rule. Total energy is the sum of potential and kinetic energy.
Which we already talked about, right?
Yeah, we already talked about that.
Okay, cool.
But here's where it gets fun. You get to come up with your own rules based on what you've observed in the simulation.
Okay.
So, for example, like, what happens to the maximum potential and kinetic energies as the initial angle increases?
Hmm.
Or how does changing the length of the string affect things?
Right.
Just think about the relationship between all these different variables.
Gotcha.
And it's not just about writing down the rules, it's about understanding those relationships.
Totally.
Like, why do they exist?
Yeah, exactly.
What are the underlying principles that are at play here?
Here's a hint. One rule that you might come up with is that a longer pendulum will have a longer period, meaning it will swing back and forth more slowly.
Right.
Why do you think that is?
Right.
Think about how that length affects the distance the bob has to travel.
All right, one more challenge for you before we move on. The source material provides a sample EVST graph,
Okay.
which shows how the energy changes over time for a particular pendulum swing.
Gotcha.
Your challenge is to try to reproduce this exact graph using the simulation.
Fun.
You're going to need to experiment with different initial angles and lengths to find the perfect combination.
So a little bit of trial and error.
Yeah, this might take a little bit of trial and error, but that's all part of the fun of scientific exploration.
Exactly.
Pay close attention to how the graph changes as you adjust the variables.
Mm-hmm.
What do you notice?
Yeah. Are there any patterns emerging?
So we've covered the basics of the pendulum,
Yeah.
how energy transforms within it.
Mm-hmm.
We've even dabbled in a little bit of calculation and
Right.
rule making.
Awesome.
You're well on your way to becoming a pendulum pro.
Totally.
But there's still so much more to explore.
Oh, yeah.
We'll be right back in a flash to dive even deeper.
Sounds good.
Stay tuned.
I'm excited.
And we're back. Hope you're ready for round 2 because we're about to take our pendulum knowledge to a whole new level.
Yeah. Things are about to get even more interesting.
Okay, so we've talked about how energy is constantly transforming between potential and kinetic.
Right, back and forth.
But there's actually another type of energy that often sneaks into the equation.
Uh-oh.
Heat.
Ah.
So you might have noticed in the simulation that the pendulum eventually, it slows down and comes to a stop.
Right. Nothing lasts forever.
But we know energy can't just disappear, so where'd it go?
Yeah, good point.
It's been transformed into heat.
It's all about the transformation.
Okay, so it's like that old saying, energy can't be created or destroyed, it just changes form.
You got it.
So, but how does that even work?
Okay, well,
Does the pendulum, get a little bit warmer?
think about it this way. When you rub your hands together really fast, they get warm, right?
Yeah.
That's because the friction between your hands is converting some of the kinetic energy of your moving hands into thermal energy or heat.
Got it.
So it's the same principle with the pendulum.
So the friction between the string and the attachment point, and even the friction with the air, generates a little tiny bit of heat.
Exactly. Yeah.
Okay, I'm starting to get it.
It might not always be noticeable with a simple pendulum, just because the amount of heat generated is really tiny.
Right.
But it's still a good illustration of how energy transformations can be subtle.
Yeah.
And sometimes, we don't even see them happening.
Right, so even though the pendulum eventually stops swinging, that initial energy that we gave hasn't just vanished, it's just spread out as heat
It's still out there.
in the surrounding environment.
Exactly.
It's crazy.
That's a really important point.
Mm.
It highlights that while energy is always conserved, the form that it takes really matters.
Okay.
Because we want to use energy in ways that are useful to us, right? And not just let it all escape as this low-grade heat that we can't easily harness.
Right. So this makes me think back to that recreating the graph challenge from earlier.
Oh, yeah.
Did you have any luck matching that sample EVST graph in the simulation?
That was a tricky one. It really, forces you to think about how sensitive these energy transformations are to the starting conditions. Even a tiny change in that initial angle or the length can have a big impact on how that energy changes over time.
Yeah, I got pretty close,
Okay.
but I couldn't, nail it perfectly.
Oh, yeah.
It was frustrating, but also kind of cool to see how those small adjustments really make a big difference.
Yeah, that's the beauty of these simulations. They
Yeah.
let you experiment and actually see these principles in action
Right.
without having to build a real pendulum and, make all those precise measurements and adjustments.
For sure. Speaking of real-world connections,
Yeah.
the source material has some great examples of these energy transformations in everyday life. Things we see all the time,
Yeah.
but maybe haven't really thought about in terms of energy, like roller coasters.
Oh, yeah, roller coasters are a great example.
Yeah.
They're basically giant pendulums,
Right.
constantly converting potential energy into kinetic energy
Back and forth,
and back again.
climbing up those hills, whooshing down.
Exactly, as
Yeah.
they climb hills and swoop down into valleys.
And then there's the classic bouncing ball example.
Classic.
Yeah. Each time the ball hits the ground, some of that kinetic energy is converted into sound,
Right.
that satisfying thump.
Exactly.
But also heat, which is why it doesn't bounce back up to the same height every time.
It's like a little bit of the ball's energy is lost with each bounce.
Hmm.
But, of course, we know it's not truly lost.
Right.
It's just transformed into these less obvious forms.
It really is amazing how these seemingly simple concepts, like the swing of a pendulum or a bouncing ball, can reveal these big scientific truths.
Yeah, they're like little windows into the fundamental laws of the universe.
Yeah,
It makes you appreciate just how elegant and interconnected everything is.
for sure.
And, it makes me wonder, if we can understand and control these energy transformations even more precisely,
Yeah.
what incredible things could we achieve?
Now you've really got me thinking.
I know, right?
That's a perfect cliffhanger to leave our listeners with.
Ooh, they're going to be on the edge of their seats.
And we are back. We've been on quite the journey, talking about the energy of a pendulum,
We have.
exploring how it transforms, how it gets converted, how it never really disappears.
It's all about the transformation.
But before we went to break,
Yeah,
our minds were kind of blown
I know.
with this idea of harnessing that energy that's usually lost as heat.
Right.
So is that even possible, or is that just sci-fi territory?
It's definitely not sci-fi. There's a whole field of science, thermodynamics,
Okay.
that's devoted to this.
Right.
It's all about the relationships between heat and other forms of energy and how we can convert one into the other.
Okay, so we're not just letting that heat, dissipate into the ether.
Yeah.
We're talking about capturing it and using it.
Exactly.
But how do we do that?
Well,
I know geothermal energy taps into the heat from the Earth's core,
right.
but are there other ways to, do this on a smaller scale?
Absolutely. Like, imagine capturing the heat that's generated as a byproduct of, say, industrial processes,
Okay.
or even just capturing the sun's warmth more efficiently.
Right.
There's a ton of thermal energy out there just waiting to be tapped.
So are we talking about solar panels here? I know those convert sunlight into electricity.
Yeah, solar panels are definitely one way to harness the sun's energy, but there are other technologies too, like thermoelectric generators.
What are those?
These can actually directly convert temperature differences into electricity.
Okay.
So you know how one side of your pillow feels cooler than the other? Imagine if you could use that temperature difference to power your phone.
Wow, are you serious?
Yeah. That's the kind of thing we're talking about.
That's amazing.
So you could potentially use the waste heat from a factory or even a car engine
Right.
to generate electricity.
So it's like getting a second use out of energy that we would normally just waste.
Exactly. It's all about being more energy efficient, minimizing that waste, and getting the most out of the energy resources we have.
It reminds me of something the source material mentioned.
Yeah.
The concept of energy conservation.
Mhm.
We often use that phrase to mean using less energy, like
Yeah.
turning off lights when we leave a room.
Right.
But it sounds like there's a deeper meaning in the world of physics.
You're right.
Okay.
In physics, energy conservation refers to that fundamental principle that energy can't be created or destroyed,
Right.
only transformed.
Okay.
So it's not just about using less energy, but being mindful of how we're changing energy from one form to another and making sure those transformations are, actually benefiting us.
So just like with our pendulum,
Yeah.
even though it eventually stopped swinging, all that initial energy hasn't vanished. It's just been converted into those less obvious forms like heat and sound.
Exactly.
Yeah, cool.
And that's really important if we want to create sustainable energy solutions for the future.
Yeah.
It's about thinking beyond just our immediate needs and considering those long-term consequences of how we're using and transforming energy.
This entire deep dive has seriously changed how I think about energy.
I know, it's amazing, right?
It's not just some abstract concept from a textbook. It's
Right.
like literally the force behind everything around us.
It's everywhere. The swing of a pendulum, the bounce of a ball, the warmth of the sun,
Wow.
even the cells in our bodies.
It's mind-blowing to realize that these same principles govern all these completely different systems.
I know. It really highlights that elegance and the interconnectedness of the universe.
It does, and the more we explore these principles and understand them, who knows what we might be able to accomplish.
Exactly. Maybe we'll even find ways to, harness energy sources we haven't even thought of yet.
Well, on that note of limitless possibilities, we've reached the end of our deep dive into the energy of a pendulum.
It's been a great journey.
It really has been. This has been so enlightening.
I'm glad.
Thanks for joining me on this deep dive.
Of course, it was fun.
And to all of you listening out there, keep exploring, keep questioning, and never stop being curious about the world around you.
Yeah, stay curious.
Until next time, stay energized.